So our next speaker is Professor Lorenzo Maccone. He probably doesn't need any introduction, but still, he is an associate professor at the University of Pavia, Italy. And he has been associated to several prestigious institutes and laboratories across the world. His area of interest covers quantum information and quantum foundation, quantum optics, and quantum mechanics. So today he will be talking about quantum metrology of noisy spreading channels. So Professor Maccone, the floor is yours.
Thank you. Oops, I think I'm sharing the wrong screen, right? Yes. Sorry. Okay, do you see my talk?
Yes, we can see your screen.
Okay, so thank you very much for your kind invitation. So today I'm going to talk about quantum metrology of spreading channel. In particular, we will see this is interesting for the case of displacements. So this is joint work with Wojciech Goreski, who was visiting here in Pavia when we wrote this work, and Alberto Riccardi. I must say, most of the ideas came from Wojciech. So let me first remind you what quantum metrology is. And the idea of metrology is to estimate some parameter using measurements. And of course, in order to reduce the statistical errors, you always perform some averaging over a certain number of measurements. And the central limit theorem tells you that the average on the error on the average goes as 1 over square root of n. Now, in quantum metrology, we do the same thing, the estimation of parameter, but we have some increased precision using quantum effects, for example, entanglement or squeezing, and usually we get a square root of n enhancement. So the error goes as 1 over n instead of 1 over square root of n. This in the ideal case, of course. So how do measurements work? We want to estimate some parameter phi written some quantum probe system using a transformation view of phi. So we have a probe preparation where we prepare the probe in some initial state. Then we have the interaction with the system we want to measure. This interaction can be modeled like a unitary, which writes the parameter phi onto the probe, or in general, some more general transformation. Of course, the unitary is the ideal situation. And then in the end, we measure the probe and we do some data analysis. And well, the best, the idea we want to have is that we want to minimize the overlap between the input and the output state. And this, whenever we do an estimation, and this will give a good estimation procedure, we can either optimize the fidelity, so the overlap, and this usually is useful for discrimination, whether the transformation is present or not. But if we want to estimate the parameter phi, then what we really want to estimate, what we really want to optimize is the quantum Fisher information. So if we want to know what is the value of phi, this is the quantity we want to optimize. It's a sort of a metric in the space of states, and it measures the distances. Okay, so the distance between the input and output state when we travel that distance, which is related to the parameter phi we want to estimate. So quantum Fisher information is the quantity to optimize. It's usually very easy to optimize when the input state is pure state and the probe is unitary. It becomes rather complicated in the general case, but of course this is doable. Now, why do we use quantum mechanics in this measurement procedure? We want to compare how much quantum strategy gain with respect to the corresponding classical strategies. And by corresponding, I mean we use the same number of black boxes, the same number of uses of the transformation U of I, and also the same energy in the case of infinite dimensional systems. By increasing the energy, we can increase the precision arbitrarily. So in order to make a good comparison between classical and quantum strategy, of course, we need to impose that we are using the same energy in the two cases. So what are the results? Well, if we use the black boxes in parallel, classical strategies and strategies where we use entanglement only at the output. So the classical strategies are the ones where we simply repeat the estimation procedure n times. The strategy, this green box represents some entangling operation before the measurement. So this means we are doing an entangled measurement. And it turns out that in these cases, we just get the 1 over square root of n scaling of the standard quantum limit or shock noise or the central limit theorem. So you don't gain anything in this situation. But of course, quantum strategies are the ones where you do have an entanglement operation at the input or also at the output. Actually, entangling operations at the input are sufficient. And then we do get this 1 over n. And it can be proven that this is the optimal. You cannot do better than that. And that is why this is called the Heisenberg bound. And basically, the idea is that this entanglement is helping you to do the estimation. And you get a square root of n enhancement. So the entanglement of the measurement stage is useless. This was a surprise to us when we first discovered this. But what I'm talking about here in this slide, of course, is a case in which there is no noise. When there is noise, things become much more complicated because you cannot consider pure states anymore. You cannot consider unitary transformations anymore. And situations change. For example, in the presence of noise, as has been shown by other people, it is really difficult to still get this square root of n enhancement. But as we will see in this category of channels I'm going to talk about today, the spreading channels, we still do get a square root of n enhancement. Okay, I've been talking about entanglement up to now, but you can also see similar results if we use squeezing. So, for example, what we showed a few years ago is that if you take n probes, n coherent probes, instead of n coherent probes, you take a single squeeze probe, which has the same energy as these n coherent probes, and you get the same kind of advantage, 1 over n. So, of course, entanglement is one thing you can use, but also squeezing is another thing you can use. So it's more general than just entanglement. So, of course, as I was saying, the noisy case is a mess, but it's usually very complicated to see what's going on because it's much more complicated to do this optimization of the quantum visual information. But of course, in this case, it is an upper bound. So what I've shown you up to now is what is the best you can achieve. Of course, introducing noise, you cannot do better than removing noise. So what I've shown up to now is the best you can do. So now let's go to the topic of the current talk, the spreading channels. And this is a class of channels where you want to estimate this real parameter alpha, but this real parameter alpha is, there is this random rotation phi, this parameter phi, which ruins your displacement operation, but you don't care about this phi, this random phi, you want just to estimate alpha, okay? So it's sort of like a two-parameter estimation problem where the two parameters are alpha and phi, but phi is just a noise parameter. It's just something you don't care about. You just want to recover alpha. Notice that I'm not ruining this U phi is not acting on the state, on the probe state. It's acting on the channel itself. It's a sort of like a Heisenberg evolution of the channel. Okay, so it's the channel that is rotating. It's not the state which is noisy. So it's kind of different from the usual noisy quantum metrology analysis. And the idea, why are we interested in this? Because we want to estimate the displacement. The displacement operator is this type of operator here. This happens, for example, if you shine a laser on a beam splitter. This is the transformation you get on the other mode of the beam splitter. And why are we interested in this? Well, I'm collaborating with people, particle physicists who are looking for axions. And the axion, when the axion field and the electromagnetic field interact, this interaction is basically seen by the electromagnetic field as a displacement, where phi is just the phase of the axion field, and you don't care about the phase of the axion field. It's random and it's completely irrelevant. What you do care is to estimate this displacement alpha is the amplitude of the displacement. That's what you care about when you want to look at the axion field. So this is the motivation behind this kind of result. But then what we found is that the result is really general. It's not only limited to this displacement estimation. And what is known is that an optimal state for this kind of estimation is an excited Fock state, which is completely impractical, and nobody had figured out what the optimal measurement was. So what we showed is that the squeeze state is also an optimal input. Squeeze states are much more easier to create, and the fact that the squeeze state is an optimal input, that is very surprising, because if the phase phi is parallel to the squeezing, then the squeeze state really performs much worse. If the phase is orthogonal to the squeezing phase, then it performs very good. So it's difficult a priori to know whether squeeze states are good or not, but you would expect they're not, because the squeeze state performs so badly in some situations. Surprisingly, the squeeze state is still an optimum. And what we also showed is what is the optimal measurement. And the optimal measurement is really simple. It's just anti-squeezing, so again, a squeezing operation and just a simple photodetection. And this gives you the optimal measurement. So the measurement that achieves the quantum efficient operation. And the third thing we showed is that we still retain the square root of n advantage over the classical strategies. And this is surprising because this is a noisy estimation procedure. This parameter phi, which mixes the channel, is a kind of noise, and it's very difficult to get a square root of n enhancement in the noisy case, but in this case it does. And of course, we also showed that if instead of doing squeezing plus photodetection, you try to do homodyne detection, so you try to measure quadratures of the output, this does not work. And this is surprising, and it can be connected to Rayleigh's curves in imaging. I don't know if you're familiar with that. If you're not, forget about it. It's not important for this talk. But if you know about Rayleigh's curves, you know that when you are trying to distinguish two-point sources in the far field, and you try to do it by using local photodetection, you're not going to be able to do it. But if you use a better estimation strategy, then it turns out you can distinguish two-point sources. This was a very nice result by Manjit Sang and his collaborators. And similarly, something similar happens here. If you use homodyne detection, so if you use quadrature measurements, you see that in the limit of small alpha, you cannot measure, you cannot estimate alpha, even though quadrature measurements work very well for large displacements. But if you change the measurement, as I said, you use squeezing plus photodetection, then you can estimate this alpha parameter we are interested in, even in the limit of small alpha. So our results is that indeed in the limit of small alpha, so this is the regime of small alpha we're interested in, the squeeze state, this yellow line you see, goes here I'm plotting the fidelity. So if the fidelity goes down fast while alpha is increasing, this means this is a good state for estimation. And you see that the squeezed vacuum goes down very quickly as alpha increases, exactly like the coherent state. And for alpha going to zero, they go to zero with the same dependence. Okay, so they're both optimal. Instead, if you use the classical strategy by using a coherent state or a vacuum state, you see that it goes down very, very slowly. Okay, so this is a bad strategy. And similarly here, we plot the Fisher information. And again, you see that the Fisher information for small alpha of the squeeze state and of the Fock state is equal in the regime of small alpha, while the Fisher information for a coherent or a vacuum state is much lower. Okay, then for larger values of alpha, there's sometimes it's better to use the squeeze state, sometimes it's better to use the vacuum state, and there is this weird dependence. But typically, we are interested here in the regime of asymptotically small. So how do you want to do the experiment? You want to prepare the cavity, the optical cavity, where you want to estimate this displacement in a squeeze state. The phase of the squeezing is really not important, but you have to know it because you need it in the measurement strategy. And then you wait for the axion or whatever source of the displacement, which displaces the state with this random phase. And then you do an anti-squeezing. So that's why it's important to know what the phase of the squeezing was and do a photodetection of that. This is the experiment you want to do in order to estimate this, the amplitude of the displacement. Sorry, is my time over? I don't remember how much time I had to talk. Hello? Can you hear me? Hello?
Yes, 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 we can hear you.
Okay.
Go on.
When am I supposed to stop talking? Just
You have still time. You can stop like 12:50 or 13.
okay.
In 1 hour, you have still
1
24.
hour? I thought it was 30 minutes. Okay, so I'm going to talk much less than. Okay, so the conjecture is that the POVM that we had was that the POVM that projects onto the initial state is optimal for all channels that reduce the identity for this parameter alpha going to 0, which is the class that we call spreading channels. So if a channel reduces to the identity, whatever the parameter phi is, this noise parameter phi is, then we call this channel the spreading channels because it kind of spreads out the probe states. So the conjecture we had is that the POVM that projects onto the initial probe state is the optimal one. And we use the Brutus matrix, so the quantum Fisher information, to show that this conjecture is indeed true. The classical Fisher information, so the one that you obtain using this kind of POVM, is equal to the quantum Fisher information for small alpha. So the classical Fisher information is what you can actually calculate starting from a given estimation strategy. So how much information you get about the parameter alpha. Well, the quantum Fisher information is an upper bound to it. So the quantum Fisher information tells you what is the maximum information that you could get. Say that the quantum Fisher information can be achieved only for the optimal measure. So we use the quantum Fisher information to show that this conjecture indeed is true. And then we use convexity with the quantum Fisher information to show that in the limit of alpha going to 0, the noise, this parameter phi, which introduces a rotation in the channel, doesn't really matter. The quantum Fisher information considering the parameter is equal to the quantum Fisher information that is averaged by the noise parameter phi. Okay, so in the limit, this is true only in the limit alpha going to 0, the quantum Fisher information is equal to the quantum Fisher information averaged by the noise in this case. And this is true for optical displacements and in addition to this more general class, which we call spreading channels. And of course, if we are looking at the displacement estimation, in order to do a fair comparison, we need to, of course, since it's an infinite dimensional Hilbert space, we need to look at states with the same average energy. And we showed that the Fock states and the squeeze vacuum states both saturate the bound. That the Fock state was optimal was known already, but now we showed that the squeeze vacuum is optimal. So what can we do next? Well, first of all, we want to figure out, and we're working on it, what happens if we have further noise, like, for example, loss, what happens in the presence of loss. And then, of course, we want to adapt these protocols that we figured out to something that we can actually implement. And of course, doing squeezing and doing anti-squeezing is something that can be done easily. Doing photodetection, for example, is not so easy in the microwave regime where this is relevant if we want to do accent search. So that is what we're working on to now. And typically, what we do in quantum metrology is, as I said before, we compare quantum and classical strategies that use the same resources. And by resources, I mean the number of uses of the channel and the quantity of energy that we use. But of course, in practice, if you go to a lab, these might not be what are interesting to experimentalists. They want to have other figures of merit, but this, of course, depends on the specific implementation. So comparing quantum and classical strategies that use the same resources is something that you can always do. It's independent on the specific implementation you're using, but in practice, other figures of merit might be more. Okay, so I thought I had to talk about half an hour, so this is it. What did I say? I was reminding you what quantum metrology theory tells you in the noiseless case. So this typical square root of an enhancement that you can get if you compare the classical strategy with the quantum strategy. And by quantum strategies, I showed you how this refers both to entanglements between different probe states and to squeezing of the probe states. And then I've discussed the quantum Fisher information versus the fidelity as the figure of merit to optimize the estimation strategy. Typically, you use the fidelity if you want to discriminate whether the transformation is there or not, or you use the quantum Fisher information if you want not only to know whether a transformation has happened, but also to estimate some parameter of the transformation. And the idea why you're using the quantum Fisher information is that it is a sort of metric in the Hilbert space, which measures the distance between different states, which are connected by some transformation. And then I discussed the spreading channels. So this class of channels, which reduces to the identity for some parameter alpha going to 0. And this is the parameter alpha you want to estimate in the limit of small alpha. And this is relevant for various applications we're interested in. For example, axion search, but not only that. And then we showed that a good estimation strategy, which should not be too difficult to implement, is by using a squeezed input state, like a squeezed vacuum, and doing the measurement stage anti-squeezing and photodetection. So another squeezing operation and photodetection at the output state. So the take-home message of my talk is saying that squeezing is optimal to estimate displacements with random and irrelevant phase. And here is the result we published on PRL last year. And again, I should mention that this work was done in collaboration with Wojciech Górecki and Alberto Riccardi. Thank you. Thank you for your attention.
So the floor is open for question.
Can I ask a question?
Sure, go ahead.
So thank you for your talk. On your slide for conclusions, I think point number 4, it was related with squeezing plus anti-squeezing, I think.
Yes, let me go back. You mean, okay. Oh, okay, this, yes.
Yes, so squeezing, if I understood correctly, it can be achieved by spontaneous parametric down conversion. And anti-squeezing, it is, if I understood correctly, it is opposite to spontaneous parametric conversion. That means that two photons merge together and give birth to photon having double energy. Am I correct? So
actually, no.
okay.
Yes, this nomenclature, I apologize. This might be a little confusing. What I mean by anti-squeezing is, again, a squeezing transformation, but where I am squeezing the opposite quadrature. Okay, so if I'm squeezing the x quadrature, by squeezing, I mean I'm squeezing the x quadrature. So in phase space, I'm squeezing along the x direction, and I am anti-squeezing along the p direction. When I say anti-squeezing, it means I'm doing the opposite. So I'm squeezing along the p direction and anti-squeezing along the x direction. Okay, so this anti-squeezing is just another squeezing transformation, but where I've rotated the squeezing phase by pi over 2. Sorry, this I realize that this nomenclature that I use is not very clear, but this is what I mean. Okay, so both the squeezing and the anti-squeezing are actually the same kind of transformation. I'm just changing the phase of the squeezing.
Mm-hmm. So,
and as you say, yes, you can use it with the generative parametric down conversion, for example, crystal in the optical case, and there are various tricks like using JPAs and phase sensitive amplifiers in the microwave regime. So these transformations are well known both in the optical domain and in the microwave domain.
Okay, so in squeezing, you are squeezing, for example, x quadrature, and in anti-squeezing, you are de-squeezing x quadrature.
Exactly.
Am I correct? Yeah.
Yes, exactly. Okay. Yes, exactly.
Thank you.
That's exactly the point. Thank you.
So Professor Usha Devi has questions.
Okay. Thanks for a wonderful talk. I would like to know, when you said excited Fock states are optimal, but experimentally they are difficult to create. But then you go ahead with this squeeze states. So I just wanted to ask, in estimation theory, squeezing is non-classical. That is, we are all aware of it. But I wanted to know, if you have a two-mode squeeze state, it's entangled.
Yes.
Would there be, that is, would mode squeeze light do, or do you need entanglement also in this case?
Okay, here in this talk, I've been talking about one mode squeeze states, single mode squeeze states. So if I understood correctly your question, you're asking if this result holds also for the two mode squeeze states.
Yeah.
Exactly. Yes, that's a very good question. And actually, the answer is yes, we found out. We did not write it in the paper, maybe we should have. But indeed, it works also for two-mode squeezing. The problem we had with that situation is if we have two-mode squeezing, as you correctly said, this means that it's entangled, then we need to consider two modes. So we'll have one mode that goes into a cavity and an ancillary mode that goes outside the cavity, and then you have to make a joint measurement on both modes.
Mm-hmm.
So from the practical point of view, it's more complicated. Sorry?
Yeah, correct. I understand it. So that is, if you can manage with a single mode squeezed, why to go for two mode squeezed?
Yes,
and
exactly.
go
yes.
So because optimality is already achieved. That's one question.
Yes.
And another one that I have is, as far as noise is concerned, suppose we have noise, then the Fock state wouldn't be optimal. That is, even if it can produce, it won't be optimal. And even squeezed light might not be good as far as noise is concerned. So then the optimality questions, has it been addressed Would you like to comment on that for specific noisy channels?
Yes. No, this has not been addressed. We are working on it. So my collaborator, Simaraj Sadana, is doing a lot of simulations. As I said, when you put noise into these quantum metrology protocols, the situation typically becomes much more complicated. So he's working on it. He's doing a great job, I must say, but we still don't know what's going to happen. There's one thing I should point out. When I said that it's known that I said that Fock states are not very practical. Of course, everybody knows how to create the Fock state 1, so a single photon, or maybe even Fock state 2 or 3. When I say it's not practical, I mean when you go to higher numbers, like larger than 3, Fock states with larger photon numbers than 3. Whereas it's not too difficult to do squeezing with large amount of energy. But having a Fock state with large energy, that's not practical at all.
Thank you very much. Thank you.
Thank you. So there's a question in the chat. Can this method also be used for estimating the loss of a boson channel? Okay, this is a nice question. I don't know, because I don't know what happens in the presence of loss. We are working on it. But a quantum metrology protocol for estimating the loss of a boson channel is known already. I think Matteo Paris has some papers on that. So maybe this protocol might work to estimate the loss, but I doubt it, because this protocol is very good, is optimal when on the other hand. Yes, no, I see. So this protocol is good when the channel reduces to the identity when the parameter alpha goes to 0. Okay, so in the lossy case, if the transmissivity, if the reflectivity of the beam splitter, which models the loss, goes to 0, then indeed the lossy channel goes to the identity. So it might be good. I don't know. I've never thought about this. So this is a good question. Anyway, there are already quantum metrology protocols for estimating the loss. I'm not sure. I think they are from Matteo Paris's group. But you can certainly find it with some quick Google searching.
So is there any other question?
Can I ask a clarification question?
Sure.
So you were talking about loss mechanisms. So what type of loss mechanisms you think that will be relevant when considering squeezing, anti-squeezing, and then doing this phase estimation?
Yes, typically loss, when you do quantum optics, loss is a big problem also in the microwave regime. And by loss, I mean that some of the field is lost to dissipation. And a very good model for the loss is to put a beam splitter, which basically removes part of the field and dumps it to an outside mode, and couples an outside mode which is either in a thermal state, but usually in the regimes we are interested in, it's a vacuum state. Okay, so the loss, a very good model for the loss is given by introducing a beam splitter inside the system, which couples to some outside vacuum mode and just dumps part of your signal to the output. And for example, Mandel, Kelly, Kleiner, many years ago showed that there is a strict equivalence between a lossy photodetection and an ideal photodetector with preceded by a beam splitter. Okay, so this is the way we typically consider loss in these kind of systems.
Thank you.
Hello, sir. Have you checked the physical information for cat state and compass state in comparison to squeeze state and the Fock state? But would be
yes, yes, we did. Indeed, what you can find it in the appendix of our paper, maybe it's in the supplementary material. What comes out is that basically, if you have a cat state with a superposition of two coherent states, then this is a very good state for this kind of estimation, because in the worst case, if the displacement has a phase which is orthogonal to this superposition, then it performs really very well. And if it's parallel, the cat states performs never worse than the coherent state. So the good thing about the cat state is that it performs always at least as good as the coherent state, and in some cases it performs much better. And if instead of superposing two coherent states, you superpose many coherent states, so this is called multi-cat state sometimes in the literature, then you are sort of approximating Fock state. So then we know that in this case, you are approximating an optimal state. So the multi-cat state also performs very, very well. And so these situations are very good. And what do you mean by compass state? I'm not sure.
compass state is like four coherent states. So
the superposition of four coherent states.
yes, they like in phase space they are like east, south, north, west.
Yes.
So,
This is what I call the multi-cat state. Yes. So yes, also that case.
I think you are right that they are approaching for the Fock state. So if you check,
yes, if you increase the number of coherent states you are superimposing, then you sort of are approximating a Fock state.
Number fluctuation that approaches to the Fock state.
Yes. So indeed, actually, this was one of our first cases that we were trying, and we already saw that it was performing very well. So it was really, for us, it was a surprise that the squeeze states performed optimally.
Thank you, sir.
Another question in chat. There is a question in chat.
In chat, known states of photons are also known to be optimal for phase estimation. Do you consider one mode squeeze state is better experimentally? Okay, yes, I think so. I'm not an experimentalist, but I'm pretty sure that it's easier to perform, to create one mode squeeze state with high energy rather than known state with high energy. And what we showed in this paper I mentioned a few years ago, this was published in Quantum magazine. It's called, I think, Squeezing Quantum Metrology or something like that. what we showed is that one mode squeeze state performs the same. So it's comparing strategies where you have entanglement with strategies where you have squeezing with the same energy, then you get the same type of enhancement. And in that paper, we not only consider squeezing in the quantum optics, but we also consider, for example, spin squeezing, so in angular momentum, and in other situations like I think we also considered, if I remember correctly, free particles, so you can have squeezing also in that case, and other situations. So indeed, what we showed in that paper is that squeezing is usually just as good as entanglement at the noon state. And I think that typically squeezing is easier to implement in the laboratory. Thank you.
So is there any other question?
Can I ask one more question? Sorry.
Sure.
So it is
At least, I
related
mean,
with,
sure.
sorry. It is related with Fock states. So my question is, experimentally, how many Fock states one can generate? Or maybe reported?
Yes, I'm not too familiar with the experimental literature. What I can say with confidence is that given a certain energy, and here remember we are comparing strategies with the same energy, it's much easier to create a squeeze state with some energy E rather than a Fock state with the same energy. That I can say with confidence. If you're asking me what is the upper bound of the Fock states that one can produce in the lab today, I don't really know. And it also very much depends on the frequency. So if you're working in the optical domain, you're working in the microwave domain or in other situations. So I cannot really answer to that question. But for sure, I can say that it's much easier to do squeezing to produce high energy Fock states. That's certain.
Thank you.
We have still have time for 1 or 2 questions. So.
Oh, but I think I've talked more than enough.
Could you please recommend any literature on quantum Fisher information and Kramer-Rao bound for educational purposes?
Okay. So I think maybe, well, we wrote a review, which is a little bit dated, where we discussed this, but maybe a good one, which is more suited for didactic purposes, might be the one by Matteo Paris. Let me find it.
Sir, can you suggest the paper name that you said you have done the calculation in the appendix for the cat state?
For the cat state. Oh, okay. Yes, that is. Yes, this. Let me share my screen again. The paper where we did the calculation is the paper where we published this results. So, Where did it go? Okay, let's see. So it's this physical regulators 129245050. This is the paper with the spreading channels, and I have it printed here. And if you go to the appendix C, appendix C is where we did these calculations for that states. And we have more material, which is unpublished. If you're interested, just write me, and my email is up here. We can discuss. And regarding the previous question, so let me point out this very nice paper by Matteo Paris. I think this is for didactic purposes. I think this, it's quite old, but I think this contains the main results. So it's the International Journal of Quantum Information 7125. I think this is very nice for didactic purposes. It's very simply written and will be quite understandable. I'm not sure you're seeing my screen. Yes.
No.
Yes.
Okay, great.
No, I think, have you shown your screen? No, I think no.
Okay, sorry. Let me do that. Yes, sorry, I had removed my share. Okay, here it is.
Okay, thank you very much. So, if I understood correctly, you are comparing quantum feature information with fidelity. So the behavior is the same, if I understood correctly.
No. So
Okay.
what I'm saying is that what I'm comparing is if I want to see whether I found the optimal strategy, the optimal measurement strategy, then what I should compare is the quantum feature information, which gives me the Kramer bounds. So it gives me what can be achievable only with the optimal strategy. The quantum feature information should be compared with the classical feature information of that particular strategy. If the two are the same, the quantum feature is the same as the classical feature information for that measurement strategy, then I can be confident that that measurement strategy is optimal. So the feature information is just something that gives you a very rough idea whether your estimation strategy is going to work very well or not. So if the fidelity goes down very quickly, then you know that your strategy is a very good estimation strategy. So you use the fidelity just to have an idea whether a strategy is going to be good enough or not. But in order to really prove that the strategy is optimal, then you need to calculate the quantum feature and the classical feature information, because that really gives you the information that your strategy is going to tell you.
Thank you.
Sir, I have a question that in case you go take two modes or something, will asymmetry or symmetry of mode have any effect on the quantity of interest?
Sorry, can you repeat the question? I didn't get it.
I mean, if you take more than one modes, so
Yes.
asymmetry of among the modes, will that have any effect on the quantity of interest? Like the modes have some asymmetry due to detuning and something.
Okay. I don't know. Actually, that's a good question, but I'm not sure. So here we were focusing on a single mode because we want to estimate a single displacement. So of course, we can have more than one mode, as in the previous questions they were asking me what happens if we have two mode squeezing, so entanglement. And what we showed, but we didn't publish, is that this is also an optimal strategy. Maybe there's a factor of square root of 2, but apart from that, constant factor is still good. But if I understand correctly, you want to know what happens if I have a multi-mode estimation on multiple modes. And yeah, that's something we might be looking into in the future because we are interested in multi-parameter estimation. So maybe we can look into that, but right now I don't have an answer. Sorry, there's something. Please share the link in the chat. What link? Sorry.
I think the link of the paper is said.
Ah, the paper. Okay, so let me see if I can find a link of this paper. Let me do this. Yes, here it is. Let me also mention our own.
So if there is no other questions, so let's thank the speaker. Thank you.
Okay. Thank you. Thank you very much.